So welcome back to our next lecture in General Relativity, Introduction for Physics students. We're going to look at rotating relativistic frames of reference. We're interested in establishing the existence of apparent or virtual forces and see how they come into the description of relativity. Our emphasis here is on the metric of relativity. Okay. In the case of special relativity, remember we looked at the invariant interval of Minkowski space, and that's where we'll be picking it up. We'll be picking it up here. The generalization of the invariant interval of Minkowski space to general relativity is the invariant interval of Riemannian geometry, okay, of space-time, of curved space-time. Okay, in that case, the metric itself, okay, has components that we're going to have to compute and understand. It's not a given as it is in Minkowski space, okay, where we established that the Minkowski metric was time squared minus space squared. Okay, here we'll have a coefficient for each one of those components, and we're going to have to develop differential equations to find them. That's one of the problems of general relativity. So let's start with this. With this case, we start with the Minkowski space-time. Okay, so I'll always have a familiar space-time in this problem. I'm just going to look at it from the perspective of a rotating turntable. Okay, so it's like the problem of inertial reference frames in Newtonian physics. Okay, and let's get used to using the metric. For example, here's a familiar case. We have a moving clock. So I have my standard lab frame S, and then I have a moving frame called S prime, which is moving to the right at a velocity v, and it carries a clock at rest in it. Okay, I imagine that the origins coincide at time t equals 0, at positions x equals x prime, etc. equals 0. Okay, then for that clock, I can watch it tick, and then I can write down how the interval responds to those two measurements. So ds squared is then I'll have two ticks, and so I can look at those two ticks from the perspective of the clock in the moving frame. Okay, the time that passes in the moving frame where the clock is at rest, that's proper time. I've been calling that tau for a long time, so I'll write that down. S squared is c squared d tau squared. But then I can look at the invariant from the point of view of an observer, a lab observer in the frame S. Okay, so the clock is then moving, okay, and it's telling time. So I'll get one contribution to the metric, just ct squared, as the clock ticks away, and then x squared. Well, x is v times t, okay, so it's moving in the x direction. So dx squared becomes v squared dt squared. It's not moving in the y or z directions, okay, and so on the right hand side I get this collection. I can pull out the dt squared and get c squared minus v squared. Then I can solve for my proper time, divide through by c squared, and get d tau is equal to the square root of 1 minus v squared over c squared. That combination that we know so well from special relativity times dt. This combination, that's 1 upon gamma of special relativity fame. And I see that d tau is equal to dt divided by gamma. So I see that dt, okay, the time that the observer at rest in the frame S measures of the clock that's moving, is that dt is gamma times the proper time, and that's time dilation. Okay, the moving clock moves more slowly than it does. I'm sorry, that it tells time more slowly than it does in its proper form. Okay. So we can read off some simple physics off of the metric, and as we go through general relativity, we're going to learn to read off more and more physics from the metric. Okay, and we're going to do that in a very systematic way. We're going to develop the relationship between the equations of motion, the geodesics, okay, from the entries in the metric. Okay, and then we're going to find the wave equation and for gravity and the field equations for gravity in terms, again, of the metric. When we write down the field equations, then we'll have derivatives of the metric on one side of the equation equals energy density on the other side of the equation, and then we'll solve for given energy density, let's say, for the metric itself. So I'll solve for metrics in general relativity. Very much more sophisticated, but along the same lines of the problem we just did. We got the metric that showed us time dilation, okay, and we'll want to proceed with that. So here's a example of fiddling with the metric to express rotating reference frames, and let's see how it works. In this particular case, there's no large masses involved. There's no space-time curvature, but it's just a coordinate transformation from Minkowski space, one description of Minkowski space with Cartesian coordinates, to another description of Minkowski space from the perspective of a turntable. Well, the first thing if I'm going to discuss a turntable, let's say it's in the XY plane and it's rotating around the Z-axis, I'm going to want to use cylindrical coordinates. It's a problem with axially symmetric coordinates. So I'll have my usual angular variable here, phi. I'll have my distance to the point in the XY plane, and then finally to the point P, its height along the Z-axis. So my variables will be to exchange X, Y, and Z, the Cartesian coordinates, for R and phi and Z, as shown here. Okay, so I'll need the Euclidean spatial metric, and I write it down. I can read it right off the picture, of course, so I can do the change in coordinates, whichever way you like to do it. I always, on these simple things, I like to proceed geometrically and just see that the metric in the XY plane, well, I have radial excursions and I have angular excursions. Okay, they're in perpendicular directions. I use the Pythagorean theorem to see that dx squared plus dy squared is equal to dr squared plus r squared d phi squared. Okay, when phi changes by infinitesimal, the position at the end of r changes by r delta phi. And so I write that down, dz is the same on both sides. So then I can write down my Minkowski metric in these particular curvilinear coordinates. Okay, so now I want to consider my turntable in the xy plane. It's rotating with a given angular velocity omega. Okay, so again, just like what we did in our discussion in Newton's world, we'll introduce a variable that locates the particle in the angular direction on the turntable. Okay, so I'll introduce phi prime equals phi minus omega t. So if I fix phi prime, then I see that phi is increasing as omega. Okay, so that's how I label it. If I say I'm at a fixed phi, okay, a fixed phi prime, okay, relative to the turntable is rotating at an angular velocity omega. So phi is increasing at a rate of omega. Okay, so that's sensible coordination. Once I write that down, then for fixed omega, I can take the differentials here, and so I can come back to my statement of the metric here in terms of phi. Get rid of phi in favor of d phi prime and dt. Substitute it in, a little bit of arithmetic, and here's what I get. First, I get a term that goes like dt squared, and it looks very familiar to me. Okay, looks like my previous example, where I have 1 minus of velocity squared over c squared. And the velocity squared of the point is just omega r is the velocity. That's a transverse velocity. And so that contributes there for my coefficient of dt squared, and it's bringing into the game time dilation. But there's more here, okay? There's more here because when I make this substitution, I get cross terms as well, and I get a cross term, a mixing. Okay, when I square this fellow up, I get a mixing between angle and time. And so that's over here. Okay, I keep that away from the dt squared, but I see that this stuff in parentheses is not purely spatial. Okay, there's a term which is proportional to omega, and it mixes phi prime with t. Okay, and we're going to find that in all of our studies of rotating stars in general relativity. So I wanted to bring it out now, It's just common to the kinematics of the problem, and then what we have to expect problem contributions to the metric that go like angular velocity and then the product of an angular variable and a time variable. That's going to be common, so we'll be looking for it. Okay, and there's no clear separation between time and space. Okay, but look, I can remedy that. Let's just say I want to go and write my metric as just in terms of squares of time or space. I can do that because this is just a problem. I can just this is just a problem in completing a quadratic square. Okay, I can certainly make a linear superposition of time and phi prime such that I never see mixing, and we're going to do that. But I'm not going to do it by algebra. I'm going to do it by thinking about the special relativity involved. So can we diagonalize ds squared? That is, introduce a new time variable, okay, so that the metric splits cleanly into a piece which just depends upon time and another piece that just depends upon space. Get rid of that mixed term. Okay. I can do it by simple algebra. I'll leave that to you. It's just a problem of completing a square. Big deal. Okay. Instead, let's think about what's happening. Well, why did we get this mixing in the first place? Well, think about clocks at different angular positions. This angular position phi 1 and this angular position phi 2. Okay, they're swinging around one another. Okay, well, this reminds me of a problem in special relativity where I have clocks which are moving in a frame s prime and they're separated by a distance x prime. Okay, and when I observe those clocks from the perspective of the lamp frame, I know that there's relativity of simultaneity. Okay, clocks which are synchronized in one frame and separated by a distance along the length are not synchronized in another frame, and I know how to compute the lack of synchronarity. Okay, I have the Lorentz transformations, or just a handy specialization of them to attack this particular problem called the relativity of simultaneity. So we can imagine that these 2 points are very close to one another, so that at any particular instant, I can imagine an instantaneous frame coming along here, okay, in which both clocks are instantaneously at rest. They're moving at a velocity given by omega r, okay, and they're not synchronized. Well, how much are they out of synchronization? Well, I flip back to my special relativity textbook and I look it up, and I see that the lack of synchronization will be the distance that they're displaced in the moving frame times the velocity times 2 factors of gamma. One factor of gamma for the Lorentz contraction, okay, between the 2 points as observed from the inertial frame, and another factor of gamma, okay, from time dilation. Okay, so this is the lack of synchronization in T. If you're at all rusty about that, just go back to special relativity and look it up. It's also, we really take it apart in the supplementary lecture. Okay, I take it apart, make a longer discussion of this term than I do here. I'm just pointing out the factors here. We discuss it a little bit more in the lectures, and of course it's done very thoroughly in the early stages of special relativity, because I have to understand this to understand special relativity. So this is the lack of synchronization. So it compels me to therefore try a new time variable which accounts for this lack of synchronization. Okay, and so that's what I do. I take my dt prime variable, I write it as a dt corrected for the lack of synchronization. Plug that into the metric, and lo and behold, that's exactly the right transformation to complete the squares. Okay, and so then I'll find that ds squared is equal to a dt squared term, which I already wrote down, that expresses time dilation of a moving point at fixed r, theta prime and z, and then I'll have a purely spatial part, which goes like dr squared, and in term that goes like d phi prime squared, the angular difference in the moving frame, and it comes with a factor here that looks a lot like Lorentz contraction. Okay, it's my 1 minus v squared over c squared, except it's downstairs, and then plus d squared. So there you have it. Okay, it's a relatively complicated metric. What does it describe? Well, it describes Goodhall-Minkowski space from the perspective of a non-inertial reference frame, a rotating reference frame. And we see that it has some very curious features. Well, one of the things I had to tell this formula, of course, is that your special relativity, velocities can't be bigger than c. Okay, so I have to restrict myself to those values of r squared such that omega squared, so that omega r is less than c. Okay, so I avoid a 0 here and an infinity over here. But I do see something here. I see that when I make a change to what seems to be a nice coordinate system, I generate what's called coordinate singularities. They're slightly unphysical here because I can't reach a 0 here or an infinity here because of the speed limit, but I can get awfully close. Okay, and so I see that this particular reference frame can have its limitations. In particular, I can't parameterize all of Minkowski space from the perspective of a turntable. Okay, because I can't go out further than a particular r corresponding to omega r equals c. So that's the best I can do, but it's worthwhile, and we're going to see metrics like this later, and we're going to get used to the fact that metrics have coefficients which depend upon r and various parameters. Okay, we'll have problems where the coefficients depend upon t as well. We'll be studying problems of gravitational waves, and the waves are going to show up in the metric. Okay, they'll change the distances between freely floating points, and so we'll have that here. Okay, and so I'll be writing down metrics in that more general way as we go. These coordinates are nice, they're orthogonal, I don't have any cross terms, and space and time is separated. But it's just plain old Minkowski space reimagined. And it comes with a few caveats. Okay, and that's the way it is. Okay, so we'll pick that up later. Let's keep moving. I want to talk about some real physical effects, and the physical effects I'm interested in here are tidal forces and non-Euclidean geometry. So we mentioned the equivalence principle, and we discussed a couple of illustrations about it, and we also indicated that it's limited in its applicability to uniform gravitational fields. Okay, so a non-uniform gravitational field, the equivalence principle holds only locally. We want to ask ourselves, what are the leading corrections? Are they interesting, or is it just stuff? It's not just stuff, it's curvature. This is where the first corrections to the equivalence principle are, in fact, the components of the Riemann tensor, curvature tensor, and that's what we want to find out about. Well, let's find out about it by doing a Keduncan experiment. And I imagine myself here, a happy astronaut, outside of let's put me outside of Saturn or something. I'm going to go look at the satellites of Saturn because I really like them. Okay, but I'm doing an excursion outside my spaceship, and here I am subject to gravity of Saturn, and it pulls down as shown here. Okay, so I'm a falling astronaut, and I might have, okay, so I have a center of mass, I have my head up here, I have my feet down here, I have my arms over here. So relative to my center, I will feel stretched in the z direction and squeezed transversely. And you can see that happening here. You see that the G, the forces of gravity are pulling in on my hands, okay, and they're pulling my feet more than they're pulling my center of mass, and my center of mass is being pulled more than my head. So from my perspective, from my frame of reference where my center of mass is at rest, my head is getting pulled up, my feet are getting pulled down, and my hands are getting squeezed together. Okay, that's tidal forces. Okay. Okay. If I'm just looking at the vicinity of my center of mass, the equivalence principle works pretty well because G is rather uniform in that space-time vicinity. But if I go outside a little bit and consider extended objects, then I see tidal forces doing their dirt. Okay, we can make this more precise, and let's use the language of Newton the first go round. Later we use the language of Einstein when we develop more formalism. Okay, so I imagine that the astronaut carries 4 balls, like in the picture. At the center, balls above and below, and on the side and on the side. And it feels a force of gravity pulling down. And I imagine that the Newtonian gravitational potential is phi, minus gradient is the acceleration of gravity. And that's written here. I'm just writing down the acceleration of gravity is minus gradient of phi. And here's phi written for simple mass, which is spherically symmetric. Now I want to see how these various points respond. And so I'm not interested just in how my center of mass responds, but I want to look at those positions, r plus epsilon, where epsilon might point here, or here, or here, or here. So I write that down. Well, what does that mean? Well, on the left-hand side, it's easy. It's just r plus epsilon. I can do the time differentiation, pulling it through. Over here, I have gradient of phi at at these points, not the center of mass. So it's r with little corrections. So I'll expand the potential, okay, in that direction to first order using Taylor series expansion. That's what I've done. Okay, so I do that, and for phi here, I put it back in here, okay, and so, okay, and then I'll look at the equation of motion for epsilon, getting rid of the equation of motion for the center of mass. That's given by the leading terms. The first corrections I'm looking for. So I have epsilon on the left, epsilon on the right, and then perhaps corrections of higher order, which I drop. But here's the equation of motion for the first correction to the equation of motion for the center of mass. And it goes like, I see it right here, gradient, and then gradient applied to phi of r plus epsilon, and phi of r plus epsilon has a correction, which is epsilon dot gradient. So that's this term. I see that that epsilon, the equation of epsilon depends upon the second derivatives of the potential, not the first. It's not a force, it's a stress. Okay, it's a stress. So if I put in here for phi 1 upon r and just work out these derivatives in good old Cartesian coordinates, and then I get this collection over here. So by x upper k and x upper I, that's really the components of r. The components of r in the kth direction. So k might be 1, 2, or 3, x, y, or z. Okay, like that. And I'm just writing out these terms. Okay, it's straightforward. I want you to duplicate that, and it's done in the lecture. I do the arithmetic in a very straightforward way. It's just one line, okay, but it's particularly important. Where do I get the two terms? Well, I have to take gradient of 1 upon r, okay. So I'll get a 1 upon r squared term, okay, and a direction. It's a gradient, so it'll be an r squared down squared and an r direction unit vector upstairs. Then I have to take the gradient of that. I'll get two terms. I'll take the gradient of 1 upon r squared. I'll get 1 upon r to the cube. Then I have to take the gradient of the direction, okay? And so I'll get I'll get an extra term due to that. Okay, so I have these two different types of terms, and they're familiar to me. I identify a quadrupole moment. Okay, qij is 3, well, x to the I, xxi, xj minus r squared. That's the magnitude of xi, delta ij. Okay, so why do I know this? Well, I know this from electrodynamics. And I know this also from mechanics. I calculate the quadrupole moment of mass distributions in mechanics. I calculate the quadrupole moment of charge distributions in electrodynamics. And it's the second order in the displacement variables, okay, and it has this characteristic shape. Okay, now what's interesting about it is now to take the example here. Okay, in my example here, R is the position of my center of mass. It's up along the z-axis. So for R, X and Y are 0, and Z is R. Okay, so then I can come back here and write down for you the equations of motion for epsilon. Epsilon in the third direction, that will apply to this direction, and then epsilon in the transverse direction, telling me about the balls at the ends of my arms. Okay, but then I see, okay, for example, since X and Y are equal to 0, then in one of those equations, this term is absent, and so I simply get a minus R squared here, which cancels the 1 over R to the 5th. Okay, so I get 1 over R. I get 1 over R cubed just with a minus sign, and that controls epsilon in the one direction. Okay, in the one direction, and then in the three direction, then that's a different calculation, because x3, that's the z direction, j equals 3, that's the 3 direction. So I get both of these terms contributing. The 3 beats the minus 1, and I get a plus 2 in that direction. And that shows it to me. So the acceleration of the balls at the sides is attractive to the center of mass, proportional to the distance away, falling off like 1 upon R cubed. Okay, falls off quickly with R. It's a stress. And then along my lengths, the coefficient is positive. It goes like epsilon 3. So epsilon 3 is positive for the ball over my head, which tends to accelerate away from me. Okay, and then for the ball below me, it accelerates in a minus direction, again away from me. Okay, and so I feel a stretch in the z direction and a squeeze in the transverse directions. Okay. Okay, so that's useful. I see quadrupole moment. Okay, giving me these are tidal forces. Okay, and they show me the relative strengths of the forces in the two directions. I see that the stretch is twice as large as the squeeze. Okay, we'll see these patterns again. We want to see these patterns. These patterns are just general properties of quadrupole moments. Wherever I have a problem with quadrupole moments, this stuff is going to haunt me. Okay, I want to make the point that this is tidal forces. Good old tidal forces of the moon affecting the tides on the Earth. So the Earth is rotating underneath the moon, and the moon is attracting the tide. So here's the moon, here's the Earth, and here's the attraction. Okay, and so the attraction is like that. Well, that doesn't really quite look like what I plotted in the previous picture, because what I plotted in the previous picture was the equations of motion relative to the center of mass. So let's take the fact that the center of mass has acceleration in this direction and measure these other accelerations relative to it. In other words, subtract off this one. So over here, the center of mass minus the center of mass is nothing. Here I subtract off the center of mass. Okay, it's closer to the moon than this side, so when I subtract this off from this side, I get a net force outward, like that. On this side, it contributes positively. I get this force, and then doing the same on the sides, the resulting force is down. Right? If I subtract this from him, I get something basically coming down. Right? This is going in this direction. I subtract off the center mass. It comes back here. And so the result is down. Okay, and that's it. There's a quadrupole moment for you. That's the tidal force. The Earth rotates under the moon, and tidal forces make the ocean somewhat oblate. A city on the equator, for example, will then experience 2 high tides and 2 low tides every day. Why is that? Well, that's because look at the picture here. As this fellow rotates under the moon, okay, then then I see, that this point and this point are experienced twice in a 24-hour period, and similarly these points are experienced twice in every 24 hours, right? So so I'm imagining that the Earth is rotating here, and so if I'm in New York, okay, then at this point I have a high tide, come over to here, I have a low tide, come over here, I have a high tide, come over here, I have a low tide. Okay, I rotate approximately once around the under the moon in 24-hour period. There's a small correction because the moon is also rotating around the Earth, but that's once every 30-odd days. Okay, that's a correction of about half an hour, and every harbor master knows about it. But roughly speaking, I get two high tides and two low tides every day, as anyone who lives in a harbor knows. Like Newton, who was living in London, observed and observed the tides. And so we learn that therefore the quadrupole moments rotate twice as fast as the planet. So the planetary motion, the moon is going around twice. The moon goes around once in a day, and the quadrupole moment, okay, goes around twice. Well, sometimes I think about the moon is going around the Earth, but really I should say the Earth is rotating under the moon. But either way you think about it, the relevant quadrupole moment is rotating twice as fast as the relevant orbit. Okay, and we're going to see that that's because it's a second rank tensor. Is a quadrupole moment. Remember, it went like x times x, or like r squared, second rank, versus the orbit of the planet. That's a vector. So the second rank tensor will rotate at twice the speed because of the symmetries in this particular problem. It's symmetric. It's symmetric across, across any face. So the quadrupole moment rotates twice as fast as the planet itself. With the planet itself, I could color this point green, this point red, this point blue, this point white, and track its rotations in that way. But I'd see that the quadrupole moment is going around twice as fast. Okay, so that's tidal forces, and we're going to understand tidal forces and their importance to general relativity and curvature soon. And we'll get to that soon, but first we're going to discuss other applications of the equivalence principle. Okay, so I'll see you here next time.